Hello and welcome to this video about proofs in linear algebra. This list of videos is going to concentrate on proofs in linear transformations, being functions that map vectors to other vectors. In this video we'll start by proving these properties in linear algebra. So we'll define a linear transformation to be a function between two vector spaces that have these two properties. It obeys this addition rule. And it obeys this multiplication rule, where A is defined to be the scalar of the vector spaces. So now to start proving part A of this theorem. We'll use an earlier vector space theorem to manipulate the expression inside the brackets. U can be any vector in the vector space, but it's best to use a non-zero vector. We can use the definition of linear transformations to move the zero outside of the linear transformation function. Then, because this linear transformation applied to a vector is itself a vector, we can then apply this theorem to make this expression into the zero vector, which completes part A of this theorem. Now to prove part B, which is the linear transformation applied to the negative of a vector. We can use another theorem to expand out the negative vector inside the function. Then we can use the property of linear transformations to move the negative one outside the function. Then we can apply this theorem to get the negative of the linear transformation, thus proving part B of this theorem. So now to prove part C of this theorem. It's a proof about a linear transformation applied to a sum of vectors in sigma notation. So we'll prove it by induction. We'll prove it firstly for the case where n is equal to 1. When n is equal to 1, then the sum reduces to one vector multiplied by a scalar. And we can easily move the scalar outside the function using the properties of linear transformations. And then we can pack it back up into this sigma notation. We need to do this to prove it for the case where n is equal to 1, even though it's much simpler to write the one vector by a scalar. So now we have to prove it true for n plus 1, assuming that it's true for n. We can easily break up the sum into these two expressions added together, which we can do for sigma notation. We can then break up this linear transformation into the sum of two linear transformations like this, using one of the properties that it's defined to have. Then we can manipulate each term using different properties. We can manipulate the first expression to be this because we've assumed it to be true for n. And for the second term, we can easily move the scalar outside the function because this function has this property. Then we can pack up the sum of these linear transformations into this sigma expression because it's a property of sigma notation. So we've proven it true for n plus 1 if it's true for n. So this is the last step of induction, where because it's true for n is equal to 1, then it's true for n is equal to 1 plus 1 is equal to 2, and then so on, for all natural numbers, and this completes the proof. So we've proven the whole theorem. So I hope that you've found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to post any helpful thoughts and ideas in the comments. Feel free to share this video, and thanks a lot for watching.